Okay, so uh, welcome everyone, and thank you very much for being here today. We have the pleasure to hear Dr. Viraja Khatu, who is a resident astronomer at CFHT, or the Canada France Hawaii Telescope. And today, for the CATS seminar, she's going to make an overview of the science we can do with CFHT and the capabilities of this really awesome observatory. With that, I will just leave the stage to you, Iraja, and again, thank you very much for your time.
Oh, thank you so much, Adrian. This is a very good opportunity for me to be at CATS because I remember when CATS started, I was a PhD student. And this was back when Carteria was the president of the GSC. And we wanted to have something where we could know and get to understand more about the telescope facilities that Canada is involved in. And this was during the COVID time. So coming back to this, but on the other side of the table is quite interesting. So I hope you are able to take out a lot out of this presentation. So, Canada France Hawaii Telescope, we are an observatory that stands on Mauna Kea, which is a mountain of considerable significance for the indigenous Hawaiian people. And this is a home for a lot of different native species, both flora and fauna. It has many designated sites and a lot of archaeological sites as well. So very important for the Kanaka Maoli people of Hawaii. So Hawaiian Islands, if we look at the chain of islands, there are four major ones. We are situated on the Big Island. And can you see my cursor over here? Okay, so we are on the Big Island, which is the most active part of this Hawaiian chain of islands, which hosts two active volcanoes, Mauna Loa and Kilauea. If we look at the terrain, so this is a feature that I recently discovered on Google. I did not care to explore Google that much before, but this is a terrain feature where you can actually see that the Mauna Kea, so the mountainous parts are at higher elevation than the other regions, which are pretty much at the sea level. So if you look at the Big Island, Waimea is over here. So this is the town where we have our CFHT headquarters, where I'm situated right now. This is almost at 3,000 feet, so it's not quite at the sea level. We're a little elevated, but the observatory is on top of Mauna Kea, which is at 14,000 feet, approximately 4,200 meters above the sea level. So it's not an easily accessible place, very difficult, thin atmosphere, difficult to breathe, less oxygen. So not usual working conditions on top of Mauna Kea. But that's where the observatory stands. So this is our telescope, the 3.6 meter telescope, and 3.6 meter is the primary mirror, which is housed under this enclosure. You cannot really see the primary mirror, it's kind of hidden inside. And the secondary is in this circular ring right on the top. With Canada France Hawaii Telescope, it is just over 45 years old. So it's quite an old observatory, but still very, very scientifically productive. So what can we do with a 3.6 meter telescope? And this is kind of a tricky question because it depends upon where you're located and what kind of instruments you have. So location instruments drive a lot of what we can do with a telescope facility. So if you look at where Hawaii is located in this big map, then Hawaii is like kind of in the center of the Pacific Ocean. So it's a very exotic place, a very unique place to be in, away from a lot of pollution on the mainland. And if we take a closer look, on the Big Island, then this is sort of the light pollution map. We have a lot of light coming from the eastern and western parts of the Big Island, where we have most of the major town population. Waimea is right over here, as you can see, which is a very, very small town. And by very small, I mean it's almost a village. So there's not a lot of population there, but Mauna Kea is right over here, and you can see there's not lot, absolutely not anything happening on top of Mauna Kea. So light pollution must be almost negligible if we have to really have the kind of observing conditions which are really required for astronomy. If we look at Mauna Kea is actually a shield volcano, and what that means is the airflow on top of Mauna Kea is not very turbulent. It has a laminar airflow, very smoothly flowing air, and that helps with giving a good seeing condition. So on our best nights on Mauna Kea, we have seeing of approximately 0.5 arc seconds, which is world class in as compared to any other facility in the world. And during bad nights, the scene can go as bad as 2.5. But then the laminar airflow on top of Mauna Kea is really helpful to get really good seeing conditions for really good science. So that's all about location. So if we move on to instruments, what can we really do with the instruments at CFHT? So thinking about one of the brightest targets, Sirius in the sky. So Sirius has a V band magnitude of negative 1.5. And with this kind of object, we can do very high dispersion optical spectroscopy and high resolution, and we can get high resolution data. So this is a spectrum of Sirius obtained with an exposure of 1 second. But you see, you get a signal noise of approximately 500 to 1,000 for such a bright object. Now, ESPaDOnS is our optical spectral polarimeter, which means we can also do polarimetric measurements. Polarimetric measurements are useful for measuring magnetic fields around stars and such. ESPaDOnS can go down to 16 mag in the V band with a decent exposure time. For fainter targets, the exposure time starts getting very higher. But then, okay. Yes, but then when we want to get to fainter targets, then we need to go to higher exposures. This is an example of what we can get from ESPaDOnS. This is a monitoring, actually a multi semester monitoring of these stars, nearby stars that could potentially harbor exoplanets. So with ESPaDOnS, we can do polarimetry, as I mentioned before. With polarimetry, we can get the different states of polarization, and with that, we are able to do a detailed mapping of magnetic fields around stars. So this is very useful, and the most kind of science that ESPaDOnS is used for. So going fainter than V equals 16 mag. Yes, we can do that. We only don't disperse the light that much, and that allows us to actually make use of imaging. So we have megacam or mega prime, the terminology, their words are used interchangeably. So megacam is our optical imaging instrument. And with megacam, we are not able to get the spectral resolution, but we are able to get a very good spatial scale for our observations. So this is useful when you're trying to observe extended objects, even point objects are observed with MegaCam, but it's especially useful for extended objects. We do a lot of moving target observations, and MegaCam, because of its imaging and the quality of data that it can provide, we can go down to a G band of approximately 25. So quite faint for that matter. So a few highlights from MegaCam. So Oumuamua, that an asteroid from outside our solar system. It was discovered using Pan-STARRS 1. So on the bottom left figure, what you can see is the original Pan-STARRS discovery. You can see the very faint objects inside the circle. Appears like a dot in B, which is the CFHT recovery of that object using MegaCam. And for moving target observations, we have to use non-sidereal guiding. With non-sidereal guiding, what happens is when we look at the images, the stars appear trailed because they're not tracked. So that is why the lines in B are actually stars, whereas the asteroid is a point object, which is quite amazing to see in the image. And something I forgot to mention earlier is wherever you see the symbol over here, this is a link that takes you to the information page. So when you have the slides, you can take a look at the information in greater detail. Okay, so another very recent thing, so 2024 YR4 was predicted to possibly hit the Earth. While CFHT observations were very deterministic to prove that this is not the case. It's not going to hit Earth in 2023, so we are safe. The chance of hitting the Earth was earlier around 3%, but with CFHT observations, we were able to conclude that it's only 40 parts per million. So it's a negligible chance of hitting the Earth. There was also recent news, 128 new moons of Saturn were discovered, and they were recognized by IAU. This was a multi-year program with CFHT MegaCam data. So we had quite a lot of observing going on with Saturn and its moons. What you see in the figure over here, all the colored spots are previous moon observations. And these are separated in different colored regions, which are basically identified as different regions for the moons to exist. And the crosses are the new discoveries, which are a part of the 128 new moons that were discovered for Saturn. And I see there's some conversation happening in the chat. If there are pressing questions, please feel free to unmute and ask your question. If not, just hold on to your question till the end, and then we can chat about that. Okay. So how about going in the infrared? So infrared observations are very useful when we are trying to look at stuff which is not quite bright in the optical, such as the dust. And absolutely, we can do infrared. We can actually do both near-infrared spectroscopy and imaging. So SPIRou is our newest instrument. It's a few years old now, I think several years old now. But SPIRou can go from H magnitudes of 3 to all the way down to 15. It has pretty high resolution and mostly used for radial velocity measurements. So it's optimized actually for radial velocity studies. It's again a spectropolarimeter in the infrared. So again, we can do polarimetry. We can measure magnetic field lines for different stars. The spectrum that you see here is of a blue hypergiant in this case. But SPIRou is useful, similar to ESPaDOnS, for very high resolution studies. And by very high resolution, I mean anywhere between 60 to 70K. For stars and exoplanet studies. So this is an example of what we can do with SPIRou. So this is a very, very young star system, a newly born star system, UMIC. And the artist impression over here shows the young star and the planet, which is acting as a rebel. The planet has a period of about 8.5 days. So there were test observations to measure the radius for this object, and then there were SPIRou observations which complemented to measure the mass, and they were able to study the density and that atmosphere of the exoplanet in this case. And then VirCam is our imaging instrument in the infrared. So with VirCam, we can go down to approximately 23 magnitudes in the edge band. So again, to very faint objects. And this is the Ring Nebula imaged in the infrared, and you can very nicely see the lower energy radiation which is blown out in the outer parts of this planetary nebula. This is another example of what we can do with VirCam. So this is a direct imaging of an exoplanet and its star. So this was a lot of data from different observatories was used together. So this was multivalent study of this system to understand the exoplanet. Specifically with VirCam, it was used to measure the positions precisely. That's what mostly VirCam is used for, very precise measurements, proper motions. And the next one actually shows an example of proper motions measured up to 4 milliarc second accuracy. So the right is the image, in the circle is the target, and on the left, what we can see are the positions of the object and how it moves. So it's the predicted position is shown, is fit with that curve that you see over there. So very accurate proper motion and parallax measurements can be done with VirCam. Okay, so now we become a little bit more greedy and ask for both imaging and spectroscopy together. And yes, we can absolutely do that at CFHT. We have an imaging Fourier transform spectrometer that helps us to do both imaging and spectroscopy. So this is similar to, if you think about an Ishel spectrograph, the kind of data that you get out of such an instrument. So it's in the form of a data cube. There are 2 spatial axes, X and Y, and then there is a spectral axis. And what you get is basically a spectrum for every pixel in your image. So I believe it's a 2000 by 2000, approximately 2000 by 2000 pixel CCD. So approximately 4 million spectra that you get from this instrument at one time. This is useful when you're studying, again, extended objects, but you want to study the spectroscopy of the extended objects, not just the imaging. And it is useful to actually build intensity maps in great detail. So this is a 3D reconstruction of the Crab Nebula using the intensity maps. And there's a very cool video of this. So I really encourage you to go and take a look at the link over there. This is an example, so radial velocity map for H alpha in this NGC 1275 system with good resolution. With CETEL, we are able to actually give a lot of information about what's happening with the dynamics of such systems. So this really shows a chaotic motion in this object over here. Okay, so with all of the instruments, we do pretty well in terms of the transmission. Not much that we can do in the infrared. There is absorption due to the atmosphere, mostly in the OH and water vapor lines. But for the optical filters, for Megacam, ESPaDOnS, and CATL, we have a pretty good transmission. So CFHT does have a group of instruments offering both optical and near-infrared capabilities for both imaging and spectroscopic studies, all the way from low to high resolution. And we will talk about the specific instruments a little bit more in the next talk. But the science is really what drives all of the instruments and what we can do really here at CFHT. Okay, so how can you make use of the CFHT capabilities? So remember, the C in CFHT stands for Canada. So it's pretty easy. Apply for CFHT time. You can get data, and if you have a science idea, going from the science idea to getting CFHT time and your data is a fairly long process, but certainly doable. So phase one is the first part of the proposals, where you actually do make a proposal submission. The proposals first come to CFHT. There's a technical review that we do internally at CFHT, and then the proposals are sent to the national TAC. Canada, France, Hawaii telescope. So there's Canada, France, and University of Hawaii. So they have time. Those are the three agencies. There's also some time offered to China and Taiwan. So it goes to the national tax for evaluation, all the proposals. And once the evaluations are done, they are then moved on to international TAC, which also do their rankings. So once the proposals are ranked, the decisions are announced, and the whole process takes about 2 months. When the proposal decision comes out, basically an email goes out to the PI, asking them to start filling in their phase two. And phase two is where you actually plan all the observations. So how you're going to observe the specific exposure times, the observing strategy. You want to make sure you have your weather conditions set properly and all ready and go for your observing. So program preparation is a big part of it, and that is it's an iterative process with the technical staff here at CFHT. So there are technical checks which are done continuously. And after that, when we're ready for observations, observations are done along with quality check. And then once your data are taken, we actually do pre-processing here at CFHT, and the reduced data are distributed to the PIs. Well, we also distribute raw data to the PIs. For some instruments, it happens upon request, but there is a provision to also distribute the raw data if the PIs need that. And the time frame going from when the decisions come to the data distribution is kind of variable depending upon which time of the semester you do your observations, and how long it takes to get the data processed for you. So finally, at the end of all of that process, you get an email in your inbox saying you have got data. So that's when you can start your science. So CFHT proposal cycles, there are 2 observing semesters, so we work all year round, basically. So there is an A call for proposal, so the Y stands for the year. So this, right now, we are in the 2025 A semester, which goes from February to July. But our call for 2025B has already opened. I mean, it was opened in February, and the proposals are due in about 2 days. So that is for the 2025B semester, which will start from August 2025 all the way to January 2026. So there are 2 calls which are opened every year, and you're given about a month of time to prepare for the proposal and make a submission. And there are different routes you can take. The most common one is the regular programs. Regular programs can be 1 or multiple semesters, so it can be a multi-semester regular program. And that's the usual way. The large programs are only accepted when there is a call for large programs that's sent out. And the same goes for the community surveys. And there's only one community survey that has happened till now in the history of CFHT, which I believe happened back in 2008 or something. So the large and community programs are special categories, but the most usual one is the regular programs. All of the accepted programs and those that are offered time are observed in the queue service observing mode, and we'll talk about that a little bit more in the next slide. But if you are interested and want to know more, or if you have questions, just reach out to the QSO team, and we will be happy to answer any questions. So talking about the queue service observing mode. So queue service observing mode is like a scheduled observing mode. It's not typical like the classical observing mode. So there are observations which are scheduled every night, and there is a pattern we follow to make all of that scheduling. The benefits of doing that is you don't need to travel. So you can very much relax at your own place. We have trained staff here who actually do the observations. They're called remote observers. We have 4 remote observers, and they basically have rotating shifts to do telescope observations during the nighttime. The way we schedule observations depends upon the science ranking, the proposal ranking that is done for different types of science. So based on those rankings, the higher priority ones get a priority on the telescope. We also do a lot of calibrations. So calibrations are taken for every instrument. They're taken every night, every run of the instrument. And just so that it doesn't get confusing, so see if how it works at CFHT is we have one instrument at a time, and when we want to switch to other instrument, we have an exchange to another instrument. So only one instrument at a time is used. So when we are using that instrument during a specific run, we make sure that we get calibration data, so flats, darks, whatever is required for the kind of science that is requested. And we are in constant touch with the PIs. So if there are any changes or if there are any updates to anything, then that is something that we keep iterating on. So we make sure that the observations are timed properly and the PIs get the data whenever they need. Okay, so what if you are not able to write a proposal? Well, there is no thing to worry, because CFHT archives all of its data at the Canadian Astronomy Data Center. And it's fairly simple to access a CADC. It's a public archive. You can go over there. You can have your own account and actually make use of the software tools that CADC offers, which is also a very good benefit. And we can talk a little bit more about that too. But all of the data is archived at CFHT, so there are tons of data that you can make use of starting right now. All right, so what's coming up next with CFHT? So we have our large programs. These large programs are for 2025A to 2026B, so about 2 years, 4 semesters, and they will be done with MegaCam, ESPaDOnS, and SPIRou, approximately 400 nights. The call for these large programs was announced last year, and we have the results at the link mentioned over here. We are currently trying to complete the previous large programs, which was from 2022 to 2024. We also have the community survey coming up. Well, this is something in preparation. So CFHT announced a call for community survey ideas last year, and this will be done with MegaCam and Wenaokeao. Wenaokeao is our newest engineering project we are currently working on, which combines ESPaDOnS and SPIRou together. And again, we can talk about that a little bit later. But MegaCam and Wenaokeao will be used for this community survey, which will start as early as 2027 and will be for up to 5 years. So, and as I said, earlier, CFHT only did one community survey previously, and this was from 2023 to 2029, which is called the CFHT Legacy Survey. There is a whole bunch of data from the CFHT list. There are still publications that come out from that data. So, such kind of really long and large survey has extended amount of time benefits for the community. And then we have our users meeting coming up very soon. So CFHT does a users meeting every 3 years. This year it's going to be in Quebec from 26th to 28th May. The registration deadline has not yet passed, so you're still welcome to register. The abstracts deadline is unfortunately passed. So but it's a very unique location, very exotic. So I really encourage you to register. And if you have any questions about that, if you want to hear more about it, then please feel free to email us and ask your questions. And a lot of the large programs and the community survey discussions will happen at the users meeting. There's also a chance for remote participation, I should mention. So if you're interested, you can also participate remotely and be a part of some of those discussions because that's going to stay in for a longer term. Okay, and with this, actually, I will, okay, I'll mute this. So I would like to switch gears over here and talk a little bit about education and community outreach, as I would like to call it. CFHT is involved in a lot of education and community events, very heavily, actually. We offer observatory tours. So on the top right, what you see is a picture of the Visitor Information Center during the nighttime. So there's not a lot that you can see in the image, actually, but it's basically at the acclimatization facility at 9,000 feet on Mauna Kea. So when we take visitors up for tours, we actually acclimatize over there, and then we head up to the summit. From Waimea, where we are right now, where I'm right now over here, up to the top of Mauna Kea is approximately 90 minutes. And that does not include the acclimatization time because visitors are required to acclimatize at least an hour at the WIS. On the left, what you see is a demonstration of a gravity well. So this is to show how black holes pull in matter. So this was from one of the events at the Imiloa Astronomy Center in Hilo. It was a Black Friday, and it was celebrated as a Black Hole Friday. So we from CFHT, we had myself and one of our remote observers. We were at the center. We set up this gravity well, and we had everyone come in and see how stars fall inside a black hole. So it was pretty amazing, but very fun to talk to kids about how this happens. And on the bottom right, you see a community meal. So this is at a location in Waimea. So community meals are organized for people in Waimea every 2 weeks. And CFHT and Keck, the WM Keck Observatory, which are both located in Waimea, we sponsor together twice a year such community meals. So I was at that community meal, and if in case you're wondering why I'm wearing so many jackets, it's because it's pretty cold in Waimea, even if you don't realize it. So it was very cold that day. But it's fun to be at such community events and trying to do what we can for the people. Okay, so this is from the. Okay, let me play that. Again, mute it. Sorry. Okay, so this on the left, what do you see? The two images of the truck. So this is from the Waimea Twilight Parade during Christmas time. So the truck that you see over here, this is Keck's truck, and the person that you see right over here is our executive director, Jean-Gabriel QB, who was told to be in the cart in which Santa was. So this is Santa's float. And this is our another staff member who's our accountant, Carolyn Petrowski. So he was told to be in the same float as Santa was, and this is really an honor because this was the second time in a row last year that CFHT and KEC were requested to do a Santa float. So this was KEC's truck, which was decorated at CFHT and used in the Twilight Parade. And then what we do after the Twilight Parade is a CFHT after party. So on the right, what you see is the dinner at the fireplace that's organized. It's open to the public. So it's for the community. And at the bottom, you see stargazing. So we had about 5 or 6 telescopes put out in our front yard here at CFHT on the grounds. And we had people come in and look through the telescopes. There were a lot of other events happening inside the observatory. That's how we see all the so much of lighting which is there inside. So there were a lot of activities for the kids. Ask an Astronomer booth to see how remote observing happens in the control room. So a lot of fun activities. And this Shadow the Scientist is a fairly new initiative for CFHT. We started it, I started working on, I'm leading this initiative, and I started working on this last year. So this is a worldwide program that was initiated at the University of California, Santa Cruz by Dr. Raja Guha. This is a platform basically to give underprivileged communities and in general for the entire public to see how observing happens, how astronomy happens, and how in general science happens. So it started with sessions in astronomy, but is now extended to other disciplines such as oceanography and a forest conservatory and other topics. So what we do over here at CFHT is we run sessions remotely over Zoom from the control room. So that's our headquarters office from how it looks from outside. And this is our remote observing room, our control room. So what during these sessions, we have our remote observer who sits in this chair over here, and I am in the control room as well. And we basically run the session, introduce the control room to the public, how we get started for the night, what are the different things we have to check on, what are the duties of the remote observer. And then once we have data coming in, we can show some of the data to the public and see how actually astronomy happens right at the origin. So that's kind of the idea. It's a very new program. We only ran one event yet. So that was in February. We had an event for the Wenaokeao visitor station on the mountain. So that was a group of people. There were about 50 people in attendance, which is quite a good crowd for the whiz, because it's kind of like a a rotating crowd. It's not people don't stay over there. They usually visit for the sunset, or they're visiting the mountain, so they can just stop by. And we had the session open at the Wiz, so anyone could come in, ask questions, and learn about astronomy. So there's a lot more coming up with that program. I'll be doing a poster for that at the users meeting as well. And one thing to realize is this is open for anyone. So if you are interested and are okay to be awake 12 a.m. In the night and see how observing happens at CFHT, you are more than welcome. So if you have questions or would like to be a part of these sessions, please send me an email and I'll be happy to arrange something. And with that, I'll end my presentation and would take any questions.
Mm.
Mahalo.
Thank you so much, Viraja. That was so interesting. Like it's so amazing. Like everything. Yeah. Like I do have some questions
Sure.
for you. Um, First of all, about like you showed. So you showed amazing pictures of like exoplanet imaging. I honestly did not know that was possible. Like I always thought imaging of exoplanets was impossible almost because it's so tiny and so difficult to observe. Like directly, like I've seen like animations and like GIFs of like sort of like indirect observations and that kind of stuff,
Yeah.
but like direct images like that, I'm like, wow, I never heard about this before. And do you know when this has like do you know when this has been done? Like in the two pictures you showed.
The pictures are short. I don't remember the date on top of my head, but I think there is a link. Okay, so I have to go back all the way. I think there is a link. Yes, that link will take you to the page where you can find more information. And if you're not able to find the date, just let me know and I'll dig it in and give you more information on that. But if you do like a rough digging into the image and the link there, you should be able to find a paper or something
Mhm, awesome.
that gives
So
you more.
can you share your slides afterwards?
Yes, I can.
Awesome. Yeah. Yeah. Please send them to me,
Sure,
and
I'll send them to you.
I will make them available for everyone. Thank you
Yeah,
so much. Yeah, because like you have so many links on your figures and images.
I do.
I think it would be great to actually be able to use them.
Yeah.
That's the thing.
Yeah, sure.
Does anyone have questions? Yeah, just
Yes.
go ahead.
Hi, can you hear me okay?
Yes.
Thank you so much, Raja. That was an incredible talk. A
Thank
really
you.
fantastic overview of the science. And yeah, thank you so much. Um, I was really curious, you mentioned Wenaokeao, and I was thinking, like what lies in the future for CFHT and like what's new and exciting that might be coming soon. I was curious about this because I think you mentioned it's a combination of ESPaDOnS and SPIRou, which sounds naively just a little bit challenging because one's in the optical, one's in the infrared. So could you maybe talk a little bit more about how that's going to work or what the vision is?
Sure. Yes, I'll give a very brief summary of what that is, and we can talk a little bit more about that when we do our follow-up talk. So Wenaokeao is a concept. It's a novel concept that is going to combine and when I say combine, it's basically going to put two instruments together in certain arrangement where you will be either able to observe with one of them or with both of them together at different fields. But you can still do the science simultaneously with ESPaDOnS and SPIRou. So that will be pretty unique because what that means is both are spectropolarimeters, one in the optical, one in the infrared. So if you want to extend your wavelength coverage from optical all the way to the infrared, you will be able to do that for your science. So that is what it will mean in terms of science capabilities. In terms of the actual configuration, it will be really nice to show how the arrangement works, and that is something the instrumentation side of things we'll talk about that when we do the follow-up session. But
Awesome.
does that answer your question at the
Yeah, yeah. So
quicker?
you can take observations with both instruments simultaneously, but at different fields of view, I guess. So it's more about making the observatory more efficient rather than getting, like an extra long spectral cube.
Um, Yes, but well, let me think about that. So, well, yes, but you can still use it under the same program for different targets. So, you can still have a science case where you're targeting different fields, but you're essentially doing the same kind of science. Does that make sense?
Mhm. Thank you so much. Thank you.
No problem.
I have another question for you, Viraja.
Mhm.
So in your day-to-day job as a resident astronomer, what do you find the most fulfilling, satisfying when you work at the CFHT today?
That's a great question, and I realize I did not touch upon that a lot. So as a resident astronomer at CFHT, my time is divided into several different things. So number one is actually support astronomy duties, and that includes doing reviews on the proposals, scheduling observations for nighttime observing. Whenever I am on duty, it's basically I work during the daytime, I make a schedule for the night, but then when observing happens at the night, if there are any questions or if there are any issues, then I can get a call and would have to respond to that. So that's kind of the nature of part of my job. A second part of my job is to help with any programming slash data processing slash instrument maintenance, whatever outlook that takes. And that is basically if there is data coming in from instruments, I would have to work on the pre-processing side of things. Or if I am managing an instrument, then I would have to make sure that, okay, we have everything ready for a specific instrument run. We have all the calibrations in place. The instrument is working fine. There are no unusual things about that in terms of what we can see as scientists. So that is like part of the second part of my job. And the third part of my job is doing my own research. So I have my own research time. So answering your question about what I feel most fulfilling is, I think with this job at CFHT, I'm exposed to a lot of learning, which is outside research, and that is the most fulfilling part of it. I'm just exposed to a whole new environment. Um, I mean, I had been on a short internship at Gemini before, but that was still not all the complete picture of what you can learn at an observatory. I have I have people who work on instrumentation, who work on operations, who work on software. So a lot of different expertise around me. So there's just knowledge everywhere that I can suck in basically. So learning a lot about the instrumentation and managing instrument and support astronomy part at CFHT is kind of the most fulfilling, where I'm able to learn a lot and grow my horizons beyond the research part.
Awesome. That's really awesome. Thank you so much, Viraja.
No problem.
Okay, if there are not other questions, I guess this is the end of our seminar. Thank you to everyone who attended, and this recording will be posted on YouTube tonight, hopefully. So, yeah, thank you, everyone, and thank you again, Viraja, for your precious time, and I wish you a good day in Hawaii.
Yeah, thank you so much, Adrian, and thank you everyone for attending. It was a pleasure. I was looking forward to this, and thank you so much for having CFHT on board for the CAT seminars. Thank you.
Absolutely.
Thank you
Thanks to
so much.
you.
Thank
Bye,
you.
Viraja. Bye, everyone.
Bye bye.